Alright, this is the section 3 notes, behavior of gases. So this is talking specifically about the gas laws. The first scientist we're going to talk about is Robert Boyle, or the first gas law is Boyle's law. And so Robert Boyle you're going to find out, had a lot of contributions to chemistry in general. He was a scientist that was around 1627 to 1691. He was a British scientist. And so one of the contributions that he had was that he obviously gave us this gas law. And the gas law that he gave us was the fact that if you decrease the volume of a gas, then you increase the pressure. And so it kind of really makes sense if you think about it, in the sense of, I think about it in terms of like a balloon. If you have a balloon and you take it, you know, like your typical, I'm not a very good drawer, so please don't make fun of my drawing. So you have this balloon, you know, and what happens if you take it and you smash it, meaning like you take all this balloon and you make it so that this part of the balloon's gone, so you squeeze it in. So basically you're decreasing the volume. What's happening? Well, if I take a balloon and I smash it in, it's probably going to, you know, eventually pop, right? Because you're taking all that air and you're compressing it in. And so what happens? Well, that pressure is going to go way up. So that's exactly what Boyle's law is saying. If you decrease the volume, then you're increasing the pressure. So he used that to come up with this equation. P1V1 equals P2V2. The pressure of the first thing times the volume of the first one equals the pressure of the second one times the volume of the second one. So if we have two different situations, we can figure out the pressure of the volume of one of those situations. So if I know the pressure and the volume of that first circumstance, I could figure out whether the pressure or the volume of the second circumstance. Okay, what's that mean? That's a lot of wordage. Here's an example. A weather balloon has a volume of 100 liters when it's released from sea level, where the pressure is 101 kilopascals. What will be the balloon's volume when it reaches an altitude where the pressure is 43 kilopascals? Okay, so we already know that our equation is P1V1 equals P2V2. Okay, it does not matter what pressure or what volume you use as long as you are consistent, meaning that the pressures both have to be in the same pressure measurement. Like, for example, in this problem, notice they gave you kilopascals, kilopascals. As long as they are both in kilopascals, you are fine. Okay? So, if they give you a problem where they give you one of them is in kilopascals and one of them is in ATMs, you need to convert them so that they are in the same unit. Okay? So, this one we're fine. Now, the other thing they gave you here, same thing about volume. Volume, it doesn't matter if you use liters, if you use milliliters. Of course, we're going to use metric, but anyway, as long as you are consistent. So, in this case, 100 liters. So for this one, PV1, P2, V2. Okay, so let's talk about this. Okay, so notice we have this balloon at 100 and its pressure is 101. These two things are linked. So if they're linked, that means that they go together in the problem. So I'm just going to make those the one values. So the pressure is 101 kilopascals, and the volume is 100.0 liters. Now, the other value they gave us was this 100 or 43.0 kilopascals. That's the secondary pressure, so that's your 2 value. So that's the second pressure, so 43.0 kilopascals. So notice they gave you everything but the second volume, which is what they're asking for. What is the new volume? So that's what you're going to plug in. 101 times 100 equals 43.0 times, we don't know the second volume, V2. And now you have to do your math. Multiply these two. So we're going to take 101 times 100. So 10100, or 10,100, equals 43.0 V2. I still have that on the other side. And then I just need to divide each side by 43. So divide each side by 43, and I get the non-sig fig answer is 34.8837. Now, what I do is I go back up here. You can rather go over here. I've written everything down here, or you could go back to like here where you have everything kind of, written down. And I say, okay, 101 has 3, 100, that has 4, 43 has 3, so my answer can only have 3, so the proper answer would be 200, so V2 should be 235, and volume, in this case, the unit was liters, so whatever it was for V1, it's also going to be for V2. Sorry, kind of ran out of room there, it's a big problem. 235 liters. All right, let's try another one. Okay, so again, we got our problem. I'm just going to write our formula up here. Oops, sorry, I forgot to hit pen. Helps if the teacher's on it. P1 V1 equals P2 V2. Okay, so P1 V1 P2 V2. Okay. Now, this one, a volume of helium occupies 11 liters with a pressure of 98 kilopascals. What is the new volume if the pressure drops to 36.2 atms? Okay, so helium occupies 11 liters. Now notice at 98. So these two are your ones. So the liters is 11. Your pressure is 98.0 kilopascals. The pressure then drops to 3.62 atm. And again, we're trying to find a volume. It works the same way if you're trying to find pressure. Now, look at our units though for this one. Kilopascals, atm. Before I could plug it in, remember I said you had to have the same thing. So it's up to you what you want to do. For future, I would not use kilopascals. That's just me. I like atms. There's going to be smaller numbers usually. So what I would do is I would take this kilopascals here. I'd go, okay, kilopascals. And this is why we took time to do pressure conversions. And make our conversions. And I'm going through this fast because we should be able to do this by now. And so we do the math. 98 times 1,000 divided by 101, 325. So you should get that that's equivalent to with sig figs, I'm going to have 3.967 atms. Alright, so now you have it, so you have the same units, so now you're ready to work. So now I would need to take 0.967 times 11 equals 3.62 times V2, and again, multiply these two, divide it by 3.62, so 0.967 times 11 divided by 3.62. V2 is equal to the calculator answer of 2.93839 blah blah blah, but if we go back up, 3 3, 3, I can only have 3, so 2.94, and again, look here, it's liters, liters, there you go. Okay, so that is Boyle's law. Then we have a second scientist named Charles. Charles is pretty interesting. He was around from 1746 to 1823. He was a French scientist. He was kind of interesting because he was the first person to ever take the first solo hot air balloon flight. And it was actually his gas law that kind of made hot air balloon flight even possible. Like, it's the concepts of Charles' law that, makes the whole idea of balloon, riding in a hot air balloon possible. His idea is that if the volume increases, then the temperature actually decreases. And so your idea is that if you have particles that are moving fast and you keep the container the exact same size. So, if I have this container of gas, here's your gas, okay? This container, okay, and I don't want the pressure to change at all. I want the pressure to stay absolutely the same. I don't want it to go up. I don't want it to go down. So rather, in order for that to happen, the volume has to get bigger, and the temperature, if the temperature goes up, then the volume has to get bigger. If the temperature goes down, then the volume has to go down. They're related. Now, for this one, it's very important. We have to have our temperatures in Celsius for this equation to work, or the relationship will not be correct. And notice what the relationship is. The volume of the first one over the temperature of the second one equals the volume of the second one over the temperature of the second one. So remember that all you have to do to get your temperatures in Kelvin is just add 273 to your Celsius temperatures. Okay, so let's do some practice. So as we said, I'll just write it up here. Oops, I'm going to get a pen. Okay, so V1 over T1 equals V2 over T2. Okay. Sometimes it sounds like a Star Trek thing, R2D2, but it's not. So, all right, so V1, T1, V2, T2. Okay. All right, so let's see. A 2-liter balloon at room temperature, which is 20 degrees, is placed in a refrigerator at 3 degrees. What is the volume after it cools? So again, these two are related because they come together in the problem, so you could call that 1. Again, if you wanted to call that 2, go for it. Doesn't matter as long as you keep them consistent together in the problem. Okay, so I've got 2 liters, 20 degrees Celsius, 3 degrees Celsius, volume, I don't know because it's the only one they didn't give me. Now again, before we keep going on the problem, temperature of the first one, add 273. Oops, I don't know how I moved that, but that was interesting. 273. Yeah. So that one's going to be 293. And then add 273 to this one. Sorry, I can't write a 7 today. So that one's going to be 276. And again, now I just want to write 3's. Okay, so there's all your numbers. Because remember, these have to be in Kelvin before you can start. And then now you're just ready to plug. So 2 over 293 equals V2, we don't know, over 276. All right. And so we're going to, you're just going to cross multiply. So I'm going to multiply these two. So I have 293 V2 equals, now take 2 times 276, so 276 times 2, so that's 552. Oh, I can't write over there. I was hoping I could write over there. You can't see it. Alright, hold on. Let me just see if I can go to a new page for math. Nope. Oops. Okay, let me just clear this page, okay? Sorry. Alright, so if I do, where was I? I was at 2 over 2, okay, I was at, sorry, so I was at 2 over 296 equals V2 over 276. And I had 296 V2 equals 276 times 2. So 552. Let me check my math because I'm kind of doing this fast. 276 times 2. Yeah, 552. So now I just have to divide each side by 296. So 552 divided by 296 is, okay, so that's right over here. V2 is going to be equal to 1.8648. And in fact, we're doing calculations with temperature, and so sig figs with temperature is going to be a little weird. So I'm not going to, on Charles' Law will be one of the few things that I'm not going to grade you on temperature. And I'll try to write that on the test. So here I'm just going to go, okay, just give me 1.86 liters, because remember it's liters here. So sorry I had to erase all that, but I ran out of room. So, okay. All right. Okay, let's go to the next one. One more. All right. Sorry, these are long videos, but lots of calculations. Okay, and here's a good example of why you have to, you know what, in fact, I'm not going to do the last one. If you need help on the last one, just ask, because I have to go through the whole entire thing again. So if you need help and want me to go through the last one with you personally, I will, but here you go.